Okay, and we're starting. Just want to begin by giving a slightly different definition of a basis than we had last time. Basically going to add one word in an effort to prevent confusion that might arise. So this was 4.4. Let V be a vector space. Let S equals V1, V2, V3. What are the two things that make a set a basis? S is a linearly independent set, and S spans V. What does it mean to be linearly independent?
If only the trivial solution. There's only one trivial solution, which is
Right. If you take the linear combination say equal to 0 vector, only the trivial solution exists. What does it mean to span the set? S spans V. What does that mean?
Vector in V, we can write a linear combination of S.
Right. Any vector in V, anyone in V, I can write as a linear combination of vectors in S. Here's what I wanted to change here. Instead of a set, I actually want you to add the word ordered. It's an ordered set. In other words, the order in which, in general, when you have a set, it doesn't matter what order you write things in, but in terms of a basis, it's better to think of it as an ordered set, and that's because of coordinates. Now remember, our coordinates is actually an ordered pair. There are commas that there's a first position, a second position, a third position, etc. So when you're writing a coordinate in terms of a basis, it's standard practice to have some convention for who is always the basis vector, that is the first person in the linear combination, who's the second person, who's the third person, who's the fourth person. So I want to say that they're ordered. The order in which the basis vectors are written matters. Right, so if you're looking at IJK notation in R3, you never put the J before the I, right? No one does that because you want them to line up with coordinates. So you sort of order them. Just wanted to mention that because we were talking about coordinates here also. So let's continue with the example that we started last time. So I gave you a basis. We proved before that's a basis in several other classes. So I call it basis S, and it had 3 vectors, 1, minus 1, minus 2. It also had 2, 1, 1. It also had 0, 0, 1. And then I said there's a vector in R3 according to the standard basis. Let V be in R3 be this matrix, this vector 1, 2, 3. And A was to find the coordinates of V relative to S. And we had that notation, it's just V with a subscript s. And that was the first one. Okay, so that was part A of our example. How do we go about this? How do you find coordinates? What are coordinates? Where are the coordinates of a vector? How do we define coordinates?
C1, C2, C3. It's one of
It's the coefficients of the linear combination that forms V.
There is a formula W equal R K1 U1. So it will be with this one 1, 2, 3 equal to the coefficient Q1 multiplied by the first vector, then plus K2.
Yeah, K1 or C1. So like C1 times the first one plus C2 times the second one plus C3 times the third one. That should give you V, which should be 1, 2, 3. Right? Now C1, C2, C3 is what we call Vs. This is the coordinates of V. Relative to the basis S, right? So we're not using IJK, we're thinking of our coordinate system in terms of 3 other vectors. Okay, so all this comes down to now is just solving the system.
System and then Kramer's rule.
So in general, I don't particularly care what method you use. Kramer's rule is fine. Row reduction is also fine. I don't particularly care. We know that the determinant of this will not be 0 because we have linear independence. So yeah, anything with that can work with a non-zero determinant will work here. So you basically set up that system and you would solve it. And it turns out, we've already done it, the solution ends up being -1, 1, 0. This means V with respect to S, we can think of it as the vector -1, 1, 0. And those are the coordinates of V with respect to S. Okay? So if we're not thinking in terms of IJK notation, we're thinking of something else in terms of this, whatever that means. That would be how we look at this vector. Right? So this vector 1, 2, 3, 1i plus 2j plus 3k is actually this vector in terms of these basis vectors, right? Because they're the coefficients. Part B. And as I said, to actually solve the system, I don't particularly care how you do it. Just get it solved. B asks another question. In this question, I gave you someone who lived in a space where this is the dominant coordinate system. I said find a V in R3 such that its coordinates with respect to S is actually 4, 5, 6. How do you find V? V would equal to what?
Are you using the same S?
Yeah, this same S. It's part B of the same example.
The same matrix, but so V is equal to C1, and then those things are equal to 4, 5, 6.
So I'll just set up another system like this with 4, 5, 6 right here.
Yeah. No, that's the solution. Is that the solution?
Right, this is the coordinates, this is the solution. So how do you go back? Right? This is like the guy I found over here, which means someone already solved the system and that was the answer. Now I want to go back to the other guy. How do we figure it out?
So you just use the S that you have and say that C1 would be 4, and then 1.
Exactly.
1
So you plug in, you know the coordinates. This is actually C1, C2, C3 from here. C1, C2, C3. So I'm just going to plug them in. It's 4 times 1 minus 1 minus 2 plus 5 times 2, 1, 1 plus 6 times
0, 0, 1.
0, 0, 1.
That
Which
would
means
be-
that
yes.
actually gives you the vector, or did out 14, comma 1, comma 6.
Alright, that's it.
Right? So if this guy was the guy in R3 and you change your coordinate system to this guy, that would be the vector you get. And you can go back by just undoing the solution. So that wasn't so bad. To help us with an example I'm going to do in the next section, I'm going to introduce another basis, and we're going to find coordinates with respect to that basis. Example 2, B, this is a basis. Here's the new basis we're considering, 1, 0, 1, 0, 2, 1, 1, 0, 0. Take my word for it, it's linear independent and it spans R3, right? And so that's a basis. Okay, so let's actually find, I want to compute the same vector. Find V with respect to B given that our vector is 1, 2, 3. Right? So how would I do that? Okay, how does the augmented matrix look? Right, these basis vectors just form a column. It's sort of why I write them in column notations, to kind of be suggestive. You literally just list them as they show up here in that basis. And then you set that as the answer. And you solve it however you want to solve it. Row reduction, Kramer's rule, whatever. You would end up with 1, 0, 0, 0, 1, 0, 0, 0, 1. And the answer would be 2, 1, 7. No, 2, 1, minus 1. That was a dash. I'm going to use the example with these vectors in a later section. That's why I'm introducing another basis. Doing 1, 2, 3. That's basically the idea behind bases and coordinates. That actually, and that was the last thing I wanted to do in 4.4. We're moving on to 4.5. Talking about dimension. Not going to do many computations here. Basically, I just want to give you some definitions about what we're talking about when we mention dimension. Dimension. Let B be a vector space. The dimension of B. Which you can write as DIM, brackets B, that's the notation for it, is the number of basis vectors in a basis for B. Remarks. If a basis has a finite number of vectors, then V is called
finite dimensional. It's called a finite dimensional vector space. In particular, if there are n basis vectors, n is a positive integer, then V is called n-dimensional. Otherwise, V is called infinite dimensional. Yes, infinite dimensional vector spaces are studied, but it's mostly something that math people do. Engineers and applied people won't really look at vector spaces like that, really. But they are useful in some contexts. Example, R2, R3, R, and in general Rn are finite dimensional. R2 is two-dimensional. R3 is three-dimensional. Rn in general is n-dimensional. Another important fact. Notice that in my definition here, I said it is the number of basis vectors. But we remember that bases aren't unique, so then it stands to reason, would all bases have the same number of vectors? It turns out that they do. In fact, that's a theorem we're not going to prove, I'm just going to mention it. All bases of a vector space V have the same number of vectors. So it's okay for me to say it's the number of basis vectors. No matter what basis we're using, you'll always have the same number of vectors, and so the term dimension is well defined, and it has nothing to do with the particular basis you're using. Any basis will have the same number of basis vectors, and that gives us the dimension. So that's a very important fact. Does someone have a question? Other important facts. Another theorem. Let V be n-dimensional. And what do we call this? V equals V1, V2, Vn, V a basis. Then A. If a set in V has more than n vectors, it is dependent. So this was what one of the students used in the last homework in 4.3 to say that P3, if you take more than 4 polynomials, you get a dependent set. It's basically using this theorem. and B if a set in V has less than n vectors, then it does not span V. So those are two important facts that can save you a lot of time. If you know something is three-dimensional, then there's no way that one vector or two vectors can span the set, so you've never bothered checking, right? If you have a set that has 4 or more vectors in a three-dimensional space, it's a dependent set. You won't waste your time checking whether it's dependent or not, right? This theorem actually gives you that for free. Again, not proving it, just mentioning it, because it's important.
Will you give a proof for that on the test?
No. Some more important facts. Maybe I can add it to. Just wanted to mention these two. So if you look at Pn, that has dimension n plus 1. And n has dimension n times n. Right, this is the set of all n by m matrices. This is a set of all polynomials of degree n or less. Those are the dimensions. So, just some quick facts that can help you out. Another important fact, if we have a homogeneous system, then we proved before that the solution set of a homogeneous system forms a vector space. Then the dimension of the solution space is the same as the number of free variables. Eventually we'll talk about row space, column space, null space, and all that, and that will come back to that. But that's just something you should know at this point. Example. Suppose a homogeneous system reduces to then the solution is given by, let's say this is x1, x2, x3, x4, right? So you do the reducer echelon form of that system, or yeah, that's actually reducer echelon form. What would the solution look like for that system? How do you get to the solution?
x1 minus, x1 equals minus x. If parameter is x3 by x2 4, we equal to.
What's the first thing we identify when we?
X2 and X4.
Huh?
Identify the pivots, right?
Right, you look for the pivots. Here's a pivot, here's a pivot, right? Which means the first column has a pivot, the second column has a pivot. You identify who doesn't, which is going to be these two guys. So x2 and x4 don't have pivots, so what will you do with them?
Parameters.
One is S and one is
Yeah, let them be parameters. So I said x2
S
equals s,
and that's 4T.
x4 equals t, and so this means that my x1 would be, well, remember we go from bottom rows going up. So first I'd solve for my x3,
X3 will be minus T.
minus x4, which is minus t, and my x1,
Minus S minus T.
minus S
Minus
minus 3T.
and so if I look at my solutions, x1, x2, x3, x4, what would it look like? I just start putting these guys. S minus 3t, x2 is s, s is minus t, t, which again, remember we can sort of split these guys up. So, yeah, so there's one guy that has all the s's, there's another guy that has all the t's. And so I have minus 1, 1,
0, 0. Negative 3, 0, negative 1, 1.
right. So here you see this guy here, these actually form a basis for the solution set. Hence, for example, we can say that the solution space to this system is actually two-dimensional. Solution space is 2D. Alright, so the solution space to that is a plane. Another important theorem, which again basically helps you cut down on computations. Let V be n-dimensional vector space. S is a set AV with exactly n vectors. Then S is a basis for V if and only if S is linearly independent or S spans V. The difference here than what was in the definition is the or. The thing is, once you know, if you know the dimension of the vector space in the first place, and you know that there's a set that has the same number of vectors as the dimension, then you only have to check one of the conditions, right? Either check it's linearly independent or check it spans V, because once one happens, the other will happen. So that will cut down on some of your work. So if a priori you know the dimensions of your vector space, and you have that many vectors, you only have to check one of the conditions that make it a basis, and it'll actually work out. So that's important. A couple more important facts here. Really wanted to get to the next section so we can start doing stuff. But as you can see, dimensions are sort of, it gives you some concepts that you can use to sort of get around doing some of the work. Because, you know, row reduction is kind of annoying, and that's super useful. So, 1. Every spanning set vector space is either a basis or contains a basis as a subset. Right? So once you have a set that spans your space, it's either itself a basis or it has a subset as the basis. You might have vectors in there that are dependent and you just throw them away and you get a basis.
So that basically makes it sound like spanning and bases are like equivalent, so what's the point in distinguishing them?
They're not equivalent.
Uh,
If you span and you have the number of vectors as the dimensions of your vector space, then you're a basis.
Can you span without the same number of vectors?
No. You can span with more than the vectors, but you can't span with less. And the thing is, if you span with more, you're automatically a dependent set, which means you have redundant guys there. So in that case, you can say you have a subset of those guys as a basis. In other words, you take the guys that are dependent and throw them away. And what you're left with will be a basis. So this is a way that sometimes you can have sets that can be bases, but they're too big. Other times you have sets that can be bases, but they're actually too small. So you can say every linearly independent set is either a basis or can be extended to a basis by adding more independent vectors. So if you're in a three-dimensional vector space, for example, you have a set that has two vectors, you know it can't be a basis. But if they're linearly independent, it means all you have to do is find one other basis to add to that set, and it can be a basis. All you have to do is check that that one guy that you're adding is independent to the previous two, and you will get a basis. Which is basically a theorem. There's a theorem that basically says what we say. I'm not going to write that down. Basically, once you can span a set, you can, if it's too big, you can remove vectors to get a basis. Once you have a linear independent set, if it's too small, you can throw more vectors in and make it a basis. And they state that in the theorem.
Is it the plus minus theorem?
No, the plus minus theorem would be used to prove this. Right. But it is a very useful theorem on its own. So theorem 4.5.5, note that theorem. It sort of puts these two into context, and also the plus minus theorem. There's another theorem that we should write down though. Theorem, this is 4.5.6. Let's look at subspaces. If W is a finite dimensional subspace of a vector space V, then the following are true. W is a subspace of a finite dimensional vector space. The vector space is finite. Then W must also be finite dimensional. also know that the dimension of W must be less than or equal to the dimension of the parent set. And as it turns out, W equals B if and only if the dimensions of W equals the dimensions of B. So if you take a subspace and it has the same number of dimensions as your parent set, it's actually the whole set itself. Those are the important facts that you need to know for dimensions. What about change of bases? .6. So I know we've been defining things very sort of esoterically and all that, but if you were to sort of explain it in an intuitive sense what a basis is, how would you do it, like in a phrase? What do you think it is? What is this creature we've been studying in terms of previous math classes?
A set of vectors whose like all of their linear combinations form the vector space.
Like Calc 2 student would know that? No, like elementary, what do you think of it as? Or even Calc 3. If you look at the set I and J, right, what does that mean? What is it, what would you call it?
That's what I was going to say next. It's like the two vectors that you talk in terms of those two vectors.
Okay, well what do we call those guys?
The standard.
Unit vectors?
Well, they are unit vectors. Why were they important? Like, what did they do for us?
It just shows it's two-dimensional.
Right, like, why was this something like this? Why was that meaningful? What did that mean? Like, 2 plus 3 did. 2i plus 3 did. What did that mean?
Oh, it gave you, when you add them, it creates a new vector, right? It creates, right?
Is that, when you were in Calc 3, that's how you thought of this?
Isn't it just 0.23? Like,
Right, it's a location.
it's a location.
Right? Yet an x, y, it's a coordinate. What I was looking for, it's a coordinate system. That's what right? Just I runs along the x-axis, right? J runs along the y-axis. And basically what happened was, when you give me a linear combination, what you're actually telling me was the location of a point in the plane based on those two vectors. I use these guys to talk about location. Coordinate systems. How do I find stuff? How do I locate things? Right? Bases, you can really think of them as coordinate systems. They're just a set that tells you this is how we locate things in whatever space you're in, right? So the thing is, sometimes things can get a little tricky. Or sometimes it gets tricky in the space that you're working with and you want to switch to something else. So for example, if you're working on something like a complicated integral, one you can think of like integration by substitution as a change of bases, right? So if you're doing some complicated integral in x and y, and it's sort of, you don't like it, you can actually sometimes, depending on what the region of integration looks like, switch to something like r dr d theta. Now what you actually did was it's sort of like a change of bases. There was one system that thought of things in terms of location of x and y, rectangular coordinates, right? Sometimes that was challenging, so what do? Is you go to another space where there's theta and r, right? And sometimes circles in here, when you move them over there, they turn into rectangles, right? So if I had a circle with center like x squared plus y squared equals 1, right? Then on my integrals here, I'd have something like, minus 1 to 1 minus radical of 1 minus x squared up to positive radical 1 minus x squared. Complicated, right? But then I translate here, and then this just becomes 0 to 2 pi, 0 to 1, right? Basically, I have a rectangle in r and theta, right? If theta was here and r was here, I would just have theta goes from 0 to 2 pi, and r goes from 0 to 1. The circle turns into a rectangle, right? Now somehow for this particular kind of problem, dealing with a rectangle was nicer than dealing with a circle, right? What you actually did was a change of basis. You changed the way you thought of locating points, and things work out nicer.
Wait,
right?
did we just square the circle? Because I thought that was, no, that's impossible with compass and ruler. Never mind.
Yeah, it's impossible with compass and rule, but we're not using compass and rule, we're using calculus. Right? So this is one of the reasons why bases are important, because one, they tell you how to move around in your vector space. They tell you where things are. But it's also important to be able to switch to other ways of locating something, right? So, if you have your car in your garage, you can locate it pretty easily. You can say, oh, the car is 3 feet from the right wall, and it's, in front of the tool shed, and blah, blah, blah. But once you drive your car outside your garage, and you want to tell someone where you parked your car, you're not going to describe it in terms of your garage. You're not going to say, well, it's like 23 miles from my garage on this. You're not going to do that. You're going to use a different coordinate system, something that everyone else would be using, like GPS, longitude and latitude, that sort of stuff. So the question is, if you have one way to locate something, a coordinate system that tells you where things are, but for some reason it's not convenient and you want to change, how do you actually do that? That is what 4.6 is about. It's called change of bases. So we're sort of going to look at how you'd actually do that. If I know where a vector is in terms of one coordinate system, how do I figure out where it is in terms of another coordinate system? So let's actually do that. This idea is that problem that I just mentioned. That's known as the change of basis problem. Suppose B and B prime are bases of a vector space. How are the coordinates of B sub B related to V sub B prime for a random vector in our vector space? Right? So if I know how to talk about the location of some vector in terms of one basis, how is that related to the location of that vector in response to with respect to some other basis? Right? This is called the change of basis problem. And I'm going to show you a way to solve it. And yes, it involves row reduction. Okay, so yeah, I know, right? It's like everything involves row reduction. Okay, so and here's where I want to go back to the previous example. So I'm going to show you what it is. I'm going to give you a theorem that talks about it. Then I'm going to show you a systematic way to do it. I won't have time to do all of it, but we're going to get as much as possible. Consider the last example in 4.4. Right? So remember our V was in R3. This was the guy 1, 2, 3. Now when I changed the location to be with respect to the basis S, I got -1, 1, 0. If I found its location with respect to the basis V, a different coordinate system, a different way of locating this point, I think we got 2, 1, -1. So now let's actually figure out how would we do that. How could we actually go from one to the other and know we're right? We know the answer ahead of time, which is why I did that whole second example. So here's the thing. Given, let's say I wanted to start with the location in terms of S, which is the first one we did. How would we find B, right? So pretend that we didn't know this, right? But I know the basis. I know the set of vectors that define the basis B. I know the set of vectors that define the basis S. And someone told me, according to the basis vector S, this is the location of this vector. How would you find what it is with respect to the basis B, right? So pretend we didn't know this yet, you know, and we want to figure that out. How do we get to that 2, 1, 1, 2, 1, minus 1? And what you've done in previous math classes actually gave you a hint, right? When you wanted to change from something like rectangular coordinates to polar coordinates, what did you actually change?
Basis.
Yeah, but how did you actually change it? How did you affect it? How did you know that a circle would turn into a square or whatever? You find a relationship, right? So your x and y were the coordinate guys in the rectangular coordinates, right? So all you did was you affected them. You changed them into something else, right? So the idea is, the way you locate something, if you want to change that, change the entire way you look at the whole universe, all you have to do is find the basis vectors and change those basis vectors. Once you change the basis vectors, you automatically change everything, because everything can be expressed in relation to these basis vectors. So basically what I'm going to do is, if I'm in S and I want to get to B, what I'm going to do is I'm going to change the basis vectors for S into corresponding vectors for the basis vectors for B. And then I'm going to use those guys to figure out the location. So that's basically what we're going to do. So recall S was the set 1, minus 1, minus 2. 2, 1, 1. 0, 0, 1. Just to remind you, B was the set 1, 0, 1. 0, 2, 1. 1, 0, 0. So these are two bases for R3. I know this is the location of a vector in relation to the coordinate system S. We can label these, let's say S1, S2, S3. We can call this B1, B2, B3. Okay, so what we're going to do, since we already know S, for each basis vector in S, find its corresponding coordinates with respect to B. Okay, so that's what I'm going to do. So the idea is I'm going to want to write S1 as C1 times B1 plus C2 times B2 plus C3 times B3. Right? By doing that, what I'm going to end up with, I'm going to end up setting up the system 1, 0, 1, 0, 2, 1, 1, 0, 0, and then I'm going to throw S1 on this side. It turns out that you would end up with, if I take S1 with respect to B, I end up with the vector minus 3 over 2, minus 1 over 2, 5 over 2. I do the same thing for S2. So I have 1, 0, 1, 0, 2, 0, 1, 1, 0, throw in S2, 2, 1, 1, and it turns out that when you do solve that Cramer's rule, row reduction, whatever you're fancy, if I, in relation to, with respect to B, that gave me the vector a half, 3 over 2. Then I do the same thing for S3. Right, so this is kind of like writing x equals r cosine theta, y equals r sine theta. Right, I'm just figuring out what they are in terms of the other guy. And when you solve that, you end up with S3 to be, with respect to B, to be the vector, this one's not so bad, 1, 0, minus 1. This was 0, 0. Okay? About to wrap this part up. I'll skip the notation. I'll just give you the answer and then we'll talk about it more next time. Check this out. Right? Take these 3 vectors that I just found. Throw them in a matrix. Right, so if I take, what was the first one? Minus 3 over 2, minus 1 over 2, 5 over 2. A half, 3 over 2. And what? 1, 0, negative 1. Now if I take that matrix and I multiply by the guy that I want to actually change, minus 1, 1, 0, can you guess what the answer is? That guy. Right? So it turns out you change those basis vectors and you create a matrix from the changed basis vectors. You can multiply by a vector in one space to transform into a basis in the other space without going through R3. You cut out the middleman. You go straight from basis S straight to basis B by just changing all the basis vectors of S in terms of B, and then multiplying all those vectors. This matrix, by the way, is called a transition matrix, which we'll talk about next time. For now, we'll end there. And we'll continue with 4.6 later. So homework for 4.4 and 4.5 due on Monday. And if you want to hang around, I have stuff to give back if you want to get homework or whatever.